Hey everybody, Mr. Piercy here, and what we're going to be looking at today are going to be another special segment of triangles known as perpendicular bisectors. Now we've discussed perpendicular bisectors early on in the curriculum when we were talking about just segments in general. And we practiced doing some constructions at the time that showed how you identified where the midpoint of a segment was because, well, if it's a perpendicular bisector, it must go through the midpoint of a segment at a right angle. Well, same idea is going to be used here, except because we're talking about triangles, now we have three segments to deal with, and therefore three perpendicular bisectors. And one of the interesting things about some of these segments that we're discussing is that a perpendicular bisector, if you construct all three of them inside of a triangle, they happen to intersect at the same place. Okay, now what that is meaning is that anytime I have three or more points that intersect at the same point, we would say that is known as a point of concurrency. So looking at the vocabulary here, that's where we're saying point of concurrency. In the diagram that I'm providing here, that is point D. Well, anything that intersects that goes through a point of concurrency, those are known as concurrent lines or concurrent rays or whatever the case may be. Now, even though they're not labeled, the perpendicular bisectors FD, ED, and CD, because they all intersect at the same place, those lines are they would be referred to as concurrent to each other. Now, one of the more interesting things about the point of concurrency of a triangle is that it happens to be the same distance away from all three points or all three vertices of the triangle itself. So they're equidistant. They're the same distance from each other. Or point A is the same distance from D as B is and C is. So that's what it means when things are equidistant. So make sure you get the vocabulary copy down here. I tried explaining it in the beginning of the last lesson. This is going to be a very vocabulary intensive unit. You must pay close attention to the vocabulary. Anything that I give you, it's not for my benefit, it is for your benefit. These are things that I will expect you to know. When you hear perpendicular bisector, well, you need to start thinking, well, there's a circumcenter if I'm working with a perpendicular bisector. And there's going to be several of these that we're going to be doing. So again, I'm just trying to emphasize vocabulary, vocabulary, vocabulary. It's super critical for this topic. So here are some things that if you go back and watch the demonstration video that I made, you can see where these things come from, why it worked out this way. Well, anytime that I have a perpendicular bisector of a segment, which in this case, segment CP is a perpendicular bisector of segment AB. Well, any point along the perpendicular bisector will be congruent to to endpoints, meaning that it will be the same distance away from, in this case, point A and point B. It's just one of the characteristics of perpendicular bisectors. They are always going, anything along the perpendicular bisector will be the same distance away from the endpoints of the segment that is bisecting. So in this case, we can say segment, because CP is a perpendicular bisector, it must be the same length from A as it is from B. Well, the converse of that would obviously say, well, if I have a segment that is perpendicular to another segment, so in the second diagram, we see that CP is perpendicular to AB, okay? But what we're seeing here is that we have point D being the same distance from A as it is from B. Well, then that must mean that CP has to be a perpendicular bisector of AB, because the only way that point D could be the same distance away from A and B at the same time is if it is on its perpendicular bisector. So that's what we're looking at here. We're just kind of taking the same thing that we said, we're just turning it around. This is not anything new that we've seen. What we can recognize is that if I have a theorem that is true, then we can turn it around, take the converse of the statement, and also wind up with something that's true. Now these are going to be two very important things that we're going to be practicing in this lesson. So if you have any questions about what these are saying or how they're going to be used, make sure you let me know what they are. Now let's take a look here at this example. It's telling us that segment AC, or that line AC, is a perpendicular bisector of segment BD. Well, looking at it here, if AC is a perpendicular bisector of BD, we know this and this are going to be congruent to each other. BC and DC are going to be the same. But because point A is on that bisector, it tells me that AB and AD also have to be the same. That means we can now set up an equation that says that AD has to be congruent or equal to AB, and substitute their particular expressions into their problem. So that's going to give me 4x is equal to 7x minus 6. So what I'm going to do is I'm going to subtract let me go ahead and write it down, because when I did this in class before, it caused a little bit of confusion. So here we have 4x is equal to 7x minus 6. Well, we're doing at this point as I'm subtracting 7x on both sides, which will give me negative 3x to be equal to negative 6. And now that I divide both sides with a negative 3 to get x by itself, we still wind up with a positive value. Almost never are we going to have a negative value for our answer in geometry, because in this case, x is going to be representing part of a length of a real figure, and distance can't be negative. So here we get x equal 2. So the question that we're being asked is, how long is segment AD? Well, substitute the 2 back into the 4x expression, and we see that AD is going to be 8 units long. Now here, this is a very good question. I really like this particular example because it's really making you think about the perpendicular bisector and its converse. All right, now pay again, for the time being, just pretend that the solution isn't there, because they're giving you this to help you think, well, how would you do it? Okay, but let's just try and see, can we figure it out without having to necessarily look at the solution as a guide. So here in the diagram, KN, line KN is a perpendicular bisector of segment JL. Well, if KN is a perpendicular bisector of JL, I'm going to mark those congruent to each other because it's a bisector. It cut it in half. So if it is a perpendicular bisector, then that means K, because it's on the bisector, has to be the same distance from J and from L. So those have to be the same. Now they're also showing us that J to M and from L to M are congruent. They're giving us that, saying that they're both 13 units long. So that means if we extended the bisector out, point M must be on the bisector because it's the same distance away from the endpoints of the line segment. So now let's look at the questions. What segment lengths in the diagram are equal to each other? Well, by looking at the markings, JN and LN have to be the same, JK and LK have to be the same, and it was given to us that JM and LM are the same. So those are the three sets of segments that we can conclude have to be the same based on the information in the figure. Now here off to the side, what I've shown you is that JK could also be shown congruent to LK using the leg-leg congruence theorem, just to kind of cycle that stuff back in from our last unit. So is point M on line KN? Well, obviously yes. We've already discussed it. Because M is the same distance away from point J and from point L, the only way that could happen is if it is on the same perpendicular bisector as KN is. So KN and M must be collinear. Now, these are really good questions. I really like the way that they make you think about the properties of the figure. And now, even though we're just kind of filling in the blanks here, these are very well constructed answers. Like say for instance, I asked you to answer a question like this on a quiz or a test. These are the types of solutions I would expect you to be able to give me, not just, simple sentence fragments or just numbers. I would expect you to be able to explain it is this because of this reason. Now here, I'm going to go ahead and pause now. This is where I want you guys to try answering these questions yourselves. Same idea, okay, as what we just saw. So try answering these two questions. Show me what segment lengths are equal to each other and how long is segment GH. So go ahead and answer these questions, and when you're done, come on back and check your answers against mine. Okay, so presumably you guys are doing what I'm asking you to do, and you've attempted to answer the questions already. And now you're just checking to see, okay, well, how did I do, Mr. Piercy? Well, let's say line JK is a perpendicular bisector of GH. So that means GK and HK have to be the same. If JK is a perpendicular bisector, then J must be the same distance away from G and from H. So those two segments have to be the same. And they're already showing you that from point F, it's the same distance to G and to H. So those three segments are the same also, or those two segments are the same, I should say. So we have three sets of segments that are the same, GK, HK, GJ, HJ, and where did I get the fourth one from? JK and JK, yes. That one is kind of a technicality. It is shared between them, so we could, between the two triangles, GJK and HJK, so we could include those as well. Well, how about, what is GH? How long is it? Well, because G to K and H to K, they're the same length, we can start off by saying that those two segments are congruent to each other. Somewhere I wrote my stuff. There it is. So GK must be congruent to HK. So we say 2x is equal to x plus 1, and that gives us x is being equal to 1. So to find the length of GH, well, GH is made up of GK and HK. So adding those segments together, substituting 1 in for x, gives us GH to be 4 units long. All right, so here is one of the other things that I was trying to demonstrate for you in the video that goes, that kind of goes with this. We're dealing with points of concurrency. So the segments that we're going to be dealing with, a lot of them are going to create something known as a point of concurrency. Well, they'll intersect at the same place. Well, in this case, the point of concurrency just happens to be the center of a circumscribed triangle, which means it's, a circumscribed circle, which means it goes around the figure intersecting each vertex of the triangle. So that means the distance from P to A, from P to B, and P to C should be the same. So if I take my compass here and let's see, let's try opening it up here to point, oops, wrong, that's not what I'm going to do. Open it up here to point A, that looks okay, and I am not anywhere close. What am I doing? Give myself point here, and now we're at, nope, close, close. This is so much easier to do on paper. But there we go, that's not too bad. So the point of concurrency of a triangle, circumscribed, a circumscribed circle showing that point P is the center of the circle, and so that means PA, PB, and PC, because essentially they're all the radius of the same circle, they're equal to each other. Now here, this is where they're trying to ask you to think outside of the box instead of just giving you a diagram, instead of just giving you a problem and say, hey, find x, hey, find x, hey, find x. Here they're trying to make you think about, well, how do these properties actually work now that we're dealing, talking about a point of concurrency. So here we have three people that are playing catch on a field somewhere, and they want to know, well, where should you stand? So you got three people that are there already, and now you show up. Well, you want to be the same distance away from point A, B, and C, because, I mean, you don't want to throw the ball short to one guy and then really long to another person, I guess. So we're going to, you want to be the same distance away from A, B, and C from those three people. So that means you have to essentially become the circumcenter of the triangle formed between the three people. So down here in the diagram, this is kind of what they're showing you, is that you should be right here at point D. Okay, so looking here, these are what we're going to be looking at to fill in the stuff here. You would essentially be the point of concurrency of the three perpendicular bisectors of the triangle that is created with the three friends playing catch. Now this one here, this is where I normally would ask you to go ahead and just, well, you guys try doing this one on your own and see how you do. I know when I did this in class before, trying to draw this diagram, a lot of kids had a hard time. So if you have your straight edge available, you might want to just, practice drawing some right angles, or you might want to actually do the construction to find the perpendicular bisectors. Okay, but going back to the last example, in example 3, your friend at A wants to move to a location that's the same distance as everyone else. Okay, so going back here, this person at A, well, they want to move. They want to be the same distance from everybody. So where are they going to go? Well, if he wants to be the same distance away from everybody, we're relocating where the point of concurrency is, and we're going to wind up with something that looks like this. So point D, where you were, now becomes, you're still the center of the triangle, or you're still the center of the circle, but point A wants, the guy at point, whoever A is, he wants to be this, or she, they want to be the same distance away from person B, person C, and you at D. So that makes D the center of a triangle, the center of a circle still, but instead, now we're creating an obtuse triangle between you, person B, and person C, and person A is going to wind up outside of the circle, and we're going to have something that looks like this. So he is the same distance away from person B and person C. So this is one, this is not the only way that you could do it, but this is one way that you could do it. So go ahead and try copying this diagram down into your notes, and if you have any questions about anything, let me know. I'm not going to ask you to try and do anything this vague on any assignments or anything like that, but this is just asking you to really understand the property of points being the same distance away from each other using perpendicular bisectors. So this is pretty much going to wrap it up for us today, guys. Key concepts, again, keep in mind, perpendicular bisectors of triangles, they will be they create a point of concurrency known as the circumcenter, which is the center of a circle circumscribed around the triangle. Any point that is on the perpendicular bisector must be the same distance away from the endpoints and vice versa. So if a point is the same distance away from endpoints of a segment, the only way it can do that if it is on a perpendicular bisector. So those are the three main things that we're going to be looking at today. Again, make sure you start, making flashcards or something, so that way anytime you're going to hear the words perpendicular bisector, you're automatically going to start thinking about points of concurrency, and in this case, a circumcenter. Okay, so if you have any questions about anything that you've seen here, as always, ladies and gentlemen, please make sure you give me a question, send them to me in the email, send them to me in the questions of the Google Classroom, but don't hesitate if you have questions. Again, focus on the vocabulary, focus on the properties, and you should be okay. But thanks for watching, guys, and until next time, take care and be good.